Okay, we're going to finish up our discussions of reactions of alkenes and alkynes by looking at several that we discussed in class today, or several that we mentioned we would cover in class today. They include the reactions of epoxides. We'll start there, and then we'll go on to discuss the ozonolysis reaction, followed by cyclopropionation reactions of alkenes, and finally, two different types of hydrations of alkynes, a Markovnikov hydration of alkynes, and then lastly, an anti-Markovnikov hydration of alkynes. So that'll be the order of the reactions that we cover. Let's go back to reactions of epoxides. And to begin, I think it would be worthwhile reviewing the fact that we learned recently it is possible to prepare an epoxide from an alkene using a per acid. We talked about the fact that MCPBA is one of several common per acids that are utilized. This one has some advantages, as we discussed earlier. And we showed the aeroformalism mechanism leading to the epoxide. Ultimately, the epoxide, or the oxirane, that's another acceptable term for this functional group, is a three-membered ring containing oxygen. So this is how we make epoxides, or oxiranes. And what we'd like to do now is to appreciate the fact that the epoxide, or the oxirane, is a pretty special functional group. It's special in the sense that it's quite reactive, highly reactive actually, but at the same time not so unstable that it can't be isolated. That really makes it a very useful functional group in organic synthesis. We've got something that's quite reactive but still can be crystallized if it's a solid, distilled if it's a liquid, isolated, purified. That's very, very useful from an organic chemist perspective. So here we go. Why is it that the oxirane, or the epoxide, is so reactive? Well, it has to do with the fact that we're talking about three-membered rings here. And the idealized bond angles at these carbons, these sp3 hybridized carbons, would be close to 109.5. But of course, in a three-membered ring, that's just not going to be possible. So as we've discussed in the past with cyclopropanes, there's going to be a tremendous amount of angle strain. In these and other three-membered ring compounds. What's different about the oxirane as compared to a cyclopropane is, of course, the presence of this oxygen. It's going to turn out that it will be possible to hydrolyze oxiranes to vicinal diols. So under either acidic conditions, which would be H3O plus H2O, or under basic aqueous conditions, which would be OH minus H2O, it's going to be possible to take our oxirane, and if I go ahead and reconstruct the original oxirane we had, which is the oxirane of cyclohexene, it's going to be possible to take this oxirane and prepare the corresponding vicinal diol. This vicinal diol is anti. So this is another reaction. We saw a reaction of alkenes, halogenation, which led to anti-vicinal dihalides. This is a sequence, two-step sequence, where we start with an alkene and we first prepare the oxirane, and then the oxirane can be hydrolyzed under either acidic or basic conditions to give this anti-vicinal diol. Let's look at how this reaction occurs, and ultimately how it occurs will come back to the angle strain and the special reactivity of the oxirane molecule. Let's look at the reaction condition where we have aqueous basic conditions. And under these aqueous basic conditions, we have hydroxide, which is both a nucleophile and a base. And for the purposes of this reaction, it's going to behave as a nucleophile, which means we're talking about reaction at carbon. So this angle strain in this oxirane molecule allows for strong nucleophiles, or at least good nucleophiles, to come in and behave essentially as they would in an SN2-like reaction, where they attack the carbon on the opposite side of the leaving group. The leaving group in this case is nothing more than the heteroatom of this oxirane structure. So our nucleophile comes in from the opposite side. You see I've drawn the oxirane here as though it's coming out of the plane of the paper. So my nucleophile must attack from the back side, hence the dotted line here, breaking open the carbon-oxygen bond. When this happens, you can see that I've added my OH group to the back of the molecule, and the leaving group, which doesn't leave at all because it's still attached to this carbon atom, is this oxygen, which will now be present as an oxide. More specifically, we would refer to this as an alkoxide. Since the oxygen is attached to an alkyl carbon, this is an alkoxide group. That's the alkoxide portion right there. Well, it's not going to take long for this alkoxide to recognize that there's plenty of water around under these aqueous basic conditions, and the alkoxide can grab a proton off of a water molecule in order to give me my anti-vicinal diol. So hydrolysis under aqueous basic conditions is driven by nucleophilic attack. This OH minus is a nucleophile here. Nucleophilic attack at the electrophilic carbon. Now what makes this carbon electrophilic is all very similar to us. The same sort of things that make a carbon atom that's attached to a halogen, for example, electrophilic. The oxygen is more electronegative than carbon, and so that imparts some positive charge character to the carbon through an inductive effect. Basically, the oxygen is pulling electron density out of the carbon. But what makes it even more reactive and more electrophilic is that this oxirane has got all this angle strain. And notice that when the nucleophile attacks and we break open the carbon-oxygen bond, the angle strain is gone. Now we've just got a cyclohexane which is attached to a couple of oxygen-containing functional groups. No angle strain. So energetically, this is a favorable reaction because we're breaking up the angle strain that's present in the oxirane. And that, in the end, is what's going to drive all of the oxirane chemistries. At least that's going to be a big part of the driver, the loss of this angle strain. And that's why we say it's a special functional group. Once again, you're able to prepare them, oxiranes or epoxides. You can prepare them readily. You can isolate them. But once you've got them, they'll do a whole host of reactions, including this hydrolysis reaction, to give this vicinal diol, in which the two oxygens are anti. One more thing, we started with an optically inactive starting compound. This oxirane, as I've drawn it here, is actually a meso compound. There's a stereogenic center here and here, but the molecule is nonetheless rendered achiral by virtue of a plane of symmetry. This mirror plane runs right through the middle of the molecule. This side is identical to that side, so the molecule is meso. As a meso compound, it's achiral and optically inactive. And yet, if you follow the reaction, I've prepared in the end here a compound which has two stereogenic centers and is most definitely chiral. There's no similar plane of symmetry in this anti-vicinal diol. And of course, we know that that's just an impossibility. We can't start with an optically inactive starting material, react it with optically inactive reagents, and wind up with an optically active product. And so what must be happening here is that we are in fact forming the racemic mixture. And the way that happens is simply that this OH minus can attack this carbon or this carbon, and you get those two products, which would be a pair of enantiomers, resulting with equal probability. Statistically, one is just as likely as the other. You form a racemic mixture. The racemic mixture is optically inactive. So that's how we form the vicinal, the anti-vicinal diol under aqueous basic conditions. Let's see how we form it under acidic conditions. We go back to our oxirane, which can be formed just as we discussed by reacting an alkene with a peracid such as MCPBA. And now we're going to treat this to H3O plus H2O aqueous acid type conditions. And what we're going to see is that the H3O plus is of course an acidic species, and it can protonate the oxirane oxygen such that we generate an oxonium ion. This oxonium ion is going to be a very highly reactive one, as you might imagine, even more reactive than the oxirane itself, because we've still got the three-membered ring, but now we've got this positive charge on oxygen, which makes the oxygen more behaving as though it's more electronegative, pulling even more electron density away from these carbons, making them even more electrophilic and even more susceptible to nucleophilic attack. Under these acidic conditions, we don't have a very strong base. Our strongest base, we don't have a very strong nucleophile. Our strongest nucleophile is just water. We don't have OH minus present under these acidic conditions. Water's not a very strong nucleophile, but we've got an absolutely desperate electrophile here. And so, it's going to be possible to run essentially an SN2-like reaction, once again, where water as nucleophile, a weak nucleophile as it is, normally we talk about an SN2 reaction requiring a very strong nucleophile, at least a good one, but in this particular case, the nucleophile is weak and we can get away with that because the electrophile is absolutely desperate. So our nucleophile, water, comes in from the back, and we knock off the leaving group, which, as before, doesn't actually leave because it's still tied to that carbon atom right there. And we've got, once again, this anti-vicinal diol structure. Lots of water around to pick up this acidic proton. And there's our mechanism. As before, we must be forming a racemic mixture here in order that the product is optically inactive, just as the starting material, the intermediate, and the reagents that were required for this reaction are all optically inactive. So we can make these anti-vicinal diols either under basic or acidic aqueous conditions. What are some other reactions of oxiranes? Well, as you might expect from this discussion, the oxirane is quite reactive, and it will react with a variety of species, particularly nucleophilic species. So if we have a strong nucleophile, and through our studies of SN2 reactions, we discovered lots of strong nucleophiles, like, for example, cyanide anion is a strong nucleophile. We can get them to attack the oxirane in much the same way as OH minus did, without prior protonation. We can ring open to give us structures like this. And here, if we have aqueous conditions, we would expect, as before, the alkoxide will grab a proton from water in order to produce the corresponding product, in which our nucleophile and the OH group, the oxygen coming from the starting oxirane, are once again anti with respect to one another. Well, we can just keep going. There's lots of good nucleophiles that work, lots of good nucleophiles that will ring open an oxirane, but another really good one that we've discussed in the past are the corresponding organometallics. Organometallics are very good nucleophiles. And as we progress into organic chemistry 2, we're going to utilize them as nucleophiles in a number of different reactions. In case you don't recall, if we start with an alkyl halide or an organic halide, and we treat it, for example, with magnesium 0 in the presence of ether, we can produce the corresponding Grignard reagent. We can also take that same organic halide and treat it with lithium metal to produce the corresponding organolithium. So Grignard reagents and organolithiums are two types of organometallics that we've studied in the past, and both of them are nucleophiles. And in particular, it's the carbon of the organometallic that is nucleophilic for all the reasons we've discussed in the past. The metal is very much less electronegative than carbon, and so we get bond-dipole moments which look like this. They work in the opposite direction of what we're probably accustomed to, in which the carbon is taking more than its fair share of the electron density associated with that carbon-metal bond. The metal is pushing electron density onto the carbon. If I just take one of these, let's just say the organolithium, I can actually draw a resonance form in which I place both of the electrons on the carbon atom. Doesn't really matter if this carbon belongs to a methyl group or some larger organic fragment, hence I'm using R here. It can be lots of different organic fragments which are attached to the lithium here in this polar covalent bond. This resonance form, which makes it look more like an ionic bond, is a significant resonance form in as much as it helps us to explain why the carbon atom is so nucleophilic. It looks like a nucleophile here. We have two electrons as a lone pair and a negative charge. So, what does it all mean? It means that if we take an alkene, let's start with a different alkene this time, we'll start with a trans-2-butene, and we prepare an oxirane from it. I'm going to continue to use MCPBA as my per acid of choice. Notice that, as we discussed today, the epoxidation reaction is a concerted one. Both bonds between the two carbon atoms of the alkene to the new oxygen atom are going to form at essentially the same time, hence the description as a concerted reaction. And that's going to lock in the stereochemistry. We start with trans methyl groups here, and so we're going to continue to have trans methyl groups. So we form an oxirane, and we're going to react it now with an organolithium. Let's just go ahead and choose a methyl lithium to keep it nice and simple. Let me redraw that where I show the carbon-lithium bond. And remember, these two electrons can be drawn as though they're completely on carbon in another resonance form, but I'm going to go ahead and leave the bond in place and just simply recognize that those are the nucleophilic electrons, which can come and attack the oxirane. And when they attack the oxirane, we're going to get ring opening, just as we did with other nucleophilic attacks. Now I would have two methyl groups attached at this carbon. There was, of course, a hydrogen that was there, and it's still there. I didn't show the hydrogen before, so I'm not going to show it now, but there is a hydrogen attached at this carbon and another hydrogen attached at this carbon, and they're still, of course, there. But notice that now I have two methyl groups, whereas before I only had one. The second methyl group, of course, coming from the methyl lithium. Well, in a separate second step, I would need to treat this with water. Why a separate second step? In this case, we can't use an organometallic in the presence of water, as the water would destroy the organometallic. The water is acidic compared to the highly basic organometallic compound. We talked about this in the past. When you prepare organometallics, it has to be done under very dry conditions. Otherwise, the organometallic is just protonated, in this case to give methane, and that would destroy it. So we have to run this, we have to prepare the organometallic under very dry conditions and allow it to react, in this case with our oxirane under dry conditions. And then in a separate second step, we can add water, probably as a mixture with some acid, H3O+, and that will simply protonate the alkoxide in order to give us our product, which would look like this. So in this particular case, we've produced an alcohol by reacting the oxirane with an organometallic, and we could do essentially the same reaction with a Grignard reagent, giving rise to the very same product. So the moral of the story is that oxiranes, once formed, are susceptible to nucleophilic attack, and it can be all different sorts of nucleophiles that are attacking. So those are some very important reactions of oxiranes or epoxides. And what I'd like to do now is to move to ozonolysis. Ozonolysis is an important reaction that involves ozone. Ozone is O3. Now there are lots of different resonance forms for ozone, but one of the more significant resonance forms looks something like this, where you see that we have a dipolar structure. So on one end of the molecule, the oxygen is negatively charged, and then in the middle of the molecule, the oxygen is positively charged. We refer to this as a dipole, positive and negative ends of the same molecule. If we allow ozone to react with an alkene, the pi electrons of the alkene will attack the electrophilic oxygen, which is this one. Of the two terminal oxygens, that's the most electrophilic by far. In fact, this oxygen in this dipolar resonance form looks nucleophilic. These electrons can kick onto the central oxygen, and rather than forming a carbocation, the nucleophilic oxygen can bite back down on the other carbon of the alkene in order to give us a structure that looks like this. This particular structure is not a very stable one. We can put brackets around it to indicate that it's relatively short-lived or transient. It's known as a malazinide. And the malazinide, generally speaking, rearranges to an ozonide. What's interesting about the ozonide is that it can be reductively or oxidatively worked up. We're just going to write work up right here, and we'll talk about the details of that in a few moments. The ozonide can be worked up to produce either aldehydes or ketones, or in some cases carboxylic acids. In this particular case, we have 1, 2, 3, 4, 5, 6 carbons. Those are the 6 carbons we started with in our cycloalkene. And we're going to produce at each end of the molecule 1, 2, 3, 4, 5, 6, either an aldehyde or a carboxylic acid. Now, notice that we have the 6 carbons in place just as we started. We had 6 carbons, and we form either this aldehyde group. I know we don't have a lot of familiarity with aldehydes yet, but it's a very important organic functional group, very closely related to ketones, which I'll show you in just a moment. And we're going to spend a lot of time in organic chemistry too studying the chemistry of aldehydes and ketones. If this hydrogen is instead an OH group, and I've got that in parentheses, then rather than calling it an aldehyde, we would at that point call it a carboxylic acid. And the same is true over here. Well, this reaction probably looks somewhat puzzling, but it turns out we can make pretty good sense of ozonolysis reactions if we just think about things in the right way. So I'm going to go to a simpler alkene, one that's not cyclic. We'll come back to the cyclic example in a few minutes, and I'm going to talk about how we can make sense of this ozonolysis reaction. We will have, in our first step, reaction with ozone. That's going to form the malazonide, which will rearrange to the ozonide, and then on workup it's going to give us either aldehydes or ketones. Let's just forget about the mechanism for a moment and talk about the different types of workups we can have. We can have either an oxidative workup, which means H2O2, hydrogen peroxide, or we can have a reductive workup. For our reductive workup, we've actually got a few different choices. We can work under what are essentially hydrogenation conditions, or we can use dimethyl sulfide, which is a reductive workup reagent for this reaction, or we can use zinc, usually present with an acid, something like acetic acid. We don't need to choose all of these different reductive workup conditions. But we just need to be aware that if we want to perform a reductive workup, we're going to have to choose one of those reagents. H2O2, on the other hand, is going to allow for an oxidative workup. So you see what we're doing is we're performing an ozonolysis, or we're adding ozone in the first step, and then in the second step we're choosing a workup condition, either oxidative or reductive. Now it turns out in this particular case, with this particular alkene, in both cases, whether we use an oxidative workup or a reductive workup, we're going to get the exact same result. And here's how we can sort of quickly work our way through this reaction, at least mentally, in order to demonstrate to ourselves what the products are going to look like. During the course of this ozonolysis reaction, as our prior example demonstrated, we basically break the carbon-carbon double bond. And that occurs in a few steps, first through formation of the malazonide and then rearrangement to the ozonide, and then eventually the ozonide on workup conditions breaks, and the alkene breaks into 2 pieces. In the case of this cyclohexene, those 2 pieces are still tied together because we started with a ring. But in the case of our new alkene, we don't have a ring, and when you think about breaking this carbon-carbon double bond, you really should just think about breaking it right in half, almost like you karate chopped it right in half, broke it into 2 pieces. Wherever there used to be a carbon-carbon double bond, you insert carbon-oxygen double bonds. So for example, look carefully at the structure of this alkene. We're going to break it right there, break the carbon-carbon double bond into 2 pieces, and what we're left with are 2 pieces that look like this. Where we used to have carbon-carbon double bonds, we now have carbon-oxygen double bonds. We've got 2 here because both halves are identical to each other, and so they both give rise to this very simple ketone structure, which in this case is acetone. You may have used acetone in the lab. Let's try a different one. Let's take this alkene, which is 1, 2, 3, 4, 5, 6. This is a trans 3 hexene. Trans 3 hexene. And let's treat it to ozonolysis conditions, which means in the first step we're going to add ozone. And now, because I have these hydrogen atoms which are attached to my alkenyl carbons, the workup is really going to matter. Let's start with a reductive workup. Remember, we've got 3 different sets of reductive workup conditions. I'm going to choose dimethyl sulfide first. So I'm going to add ozone across a double bond and then do a reductive workup. I'm going to chop the alkene in half. And when I do that, because of the symmetry in this structure, I get 2 identical pieces. They both look like this. Where I used to have a carbon-carbon double bond, chop it in half, I replace the carbon-carbon double bond with a carbon-oxygen double bond. And do you see that this piece over here would give rise to the exact same structure in this particular case? This is an aldehyde. Look at the functional group here. It's an aldehyde. Now, as long as we're under reductive workup conditions, and it doesn't matter whether we chose hydrogen in the presence of palladium or dimethyl sulfide or zinc in the presence of acetic acid as our reduction workup conditions, as long as we're under some reductive workup conditions, an aldehyde, if it forms, is going to be stable. And it's just going to stick around as an aldehyde. The difference is, however, if I took this very same alkene and instead of treating it to reductive workup conditions, I treated it to oxidative workup conditions, oxidation conditions, which would mean hydrogen peroxide in my workup, then I would initially form this very same aldehyde, but the aldehyde would continue to oxidize under these conditions all the way to a carboxylic acid. A carboxylic acid, if you look at it carefully and compare it to the aldehyde, is just a more highly oxidized functional group. Look at the carbonyl carbon, this one right here, in the aldehyde. It's got 2 bonds to oxygen, part of that carbon-oxygen carbonyl group, which is a double bond, 2 bonds in total to oxygen, whereas the carboxylic acid has those 2 bonds plus an additional bond to oxygen right there. The carboxylic acid, we say, is a more highly oxidized functional group as compared to the aldehyde, and it just turns out, as we'll discover in Organic Chemistry 2 when we study aldehydes and ketones under in a different chapter and looking at some different chemistries, we'll see that aldehydes are in fact susceptible to oxidation to carboxylic acids. So if we're working under oxidative workup conditions, we do initially form the aldehyde, but it just continues to oxidize all the way to the carboxylic acid. So we can get either an aldehyde or a carboxylic acid from this particular alkene, depending upon the workup conditions. Now, if I go back to the prior example, you'll notice that I chose an alkene in which there were no hydrogens attached to the alkene carbons, only alkyl groups. Hence, when you broke this one in half, we formed acetone, which is an example of a ketone functional group. So what's the difference between a ketone and an aldehyde? Well, a ketone has an R group attached to a carbonyl, which is in turn attached to another R group, and it can be the same as that R group or it can be different. I'll call it R prime here. Whereas an aldehyde has an R group attached to that carbonyl carbon, and it's attached to a hydrogen. And there's the difference. This aldehyde with this hydrogen here can, under oxidative workup conditions, continue to oxidize all the way to the carboxylic acid. So that's what we see when we work under oxidative workup conditions. On the other hand, if we're under reductive workup conditions, the aldehyde will simply be stable. So let's see if we've got this figured out now. Let's look at a couple of different examples. Back to our cycloalkene that we started with. If I treat this with ozone in the first step, and in the second step, hydrogen peroxide, that's an oxidative workup condition, then what I'm going to do is I'm going to break that alkene in half, and wherever I used to have carbon-carbon double bonds, I'm going to replace them with carbon-oxygen double bonds. In order to see what's going on, I'm kind of going to leave everything exactly as it was. I'll leave all the atoms in the same arrangement, and you can see what I've got is an aldehyde group here and a second aldehyde group there. Of course, the molecule would not stay in this particular conformation for too long, but in this particular conformation you can see exactly that I formed two aldehydes, but I'm under oxidative workup conditions. Under these conditions, the aldehydes are just going to be intermediates. They're going to continue to oxidize all the way to the carboxylic acid. Again, the molecule is not going to stick around in this particular conformation, but it is instructive to look at it nonetheless, because there is my product under these oxidative workup conditions. It's two acids, a total of 6 carbon atoms still. The better way to write this would be 1, 2, 3, 4, 5, 6, and at each end we have a carboxylic acid. This is probably a more reasonable conformation for this structure, but hopefully you see exactly how it's formed. Now what if I had run this same reaction where I start with my cyclohexene, and following reaction with ozone, I work under reductive workup conditions, which could be, for example, zinc acetic acid. Well, in this case, I'm going to break that carbon-carbon pi bond again, and wherever I used to have a carbon-carbon double bond, I now replace it with a carbon-oxygen double bond. And I have an aldehyde, a dial, two different aldehydes. Because I'm under reductive workup conditions, the aldehyde will be stable. That's just my final product. And again, probably the better way to draw this would be to draw 6 carbons like this, 1, 2, 3, 4, 5, 6, and to place the aldehyde groups at the ends of the molecule. Those are the same structure, just drawn in two different conformations. So that's ozonolysis. Maybe one more example of an ozonolysis reaction. Let's look at this one. This one's definitely not as symmetric as some of the others we've seen. If I were to number this for IUPAC purposes, I would find the longest chain that contains the alkene and give the alkene the lowest possible positional numbers. So the numbering would look something like this. This would be a 3-methyl. Heptene, and we have to ask ourselves, is this the E or the Z isomer? Well, looking at carbon 4, the propyl group beats the hydrogen, and at carbon 3, the ethyl group beats the methyl, so my two highest ranking groups are on opposite sides. This would be the E, 3-methyl 3-heptene. In the Z structure, the propyl group and the ethyl group would be on the same side of the carbon-carbon double bond. So this E, 3-methyl-3-heptene, can undergo an ozonolysis reaction. And we've got to choose either reductive or oxidative workup conditions. I think in this particular case I'm going to choose an oxidative workup, H2O2, which means I'm going to break my carbon-carbon double bond in half. When I break it in half, wherever I used to have a carbon-carbon double bond, I have a carbon-oxygen double bond. You see this hydrogen right here? Under these oxidative workup conditions, it's going to be oxidized all the way to an OH group, meaning that I've formed a carboxylic acid. That gives me what results from this half of the structure, plus a ketone from the other half of the structure. So you see that depending upon what alkene you choose, you can get all sorts of different products. You might get two of the same products. They could both be aldehydes, they could both be ketones, they could both be carboxylic acids, or you might get two different products if you start with an unsymmetrically substituted alkene. And the two products could be, for example, a ketone and a carboxylic acid under oxidative workup conditions, or a ketone and an aldehyde under reductive workup conditions. So that's the ozonolysis reaction. Moving right along, let's discuss a new reaction, cyclopropanation of alkenes. It turns out that we can take alkenes, and just as we made oxiranes or epoxides, we can make, or add I should say, carbons in the form of a three-membered ring in order to make new cyclopropane rings, and we call that cyclopropanation. The reagent of choice for this reaction is an interesting one. It's diazomethane, CH2N2, diazomethane.